Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Okay, in today's session, which is supposed to be a tutorial session, where we're going to discuss problem regarding Biot law, and we have done two examples to be specific, using Biot to determine magnetic field produced by filamentary current source. So we have done that, and then in this session we're going to extend further by doing examples taken from our textbook. For our first task, what we're going to do a problem from the practice exercise 7.1, which is on page 297. Okay, I'm going to read the problem loudly, and then from there we're going to solve the problem together. Okay, find H. For us, H here indicate magnetic field intensity at position 005 due to side 3 of the triangle loop in figure 7.68. Okay, so I'm going to draw the diagram so for our reference. So from there we're going to discuss how we'll be able to solve this problem. Okay, so again, what we're going to do, we're going to solve together problem from practice exercise 7.1. Okay, practice exercise 7.1. Okay, so in this problem, so let's draw first the current source. So I'm going to draw our current source. So current source so what's given here, the current is a triangle. So this is our current. So let's draw it. So this is given as y-axis, and this is as our x-axis. Okay, so the scale on the x-axis 0, 1, 2. Okay, that's the scaling, and then on the y-axis only 1. Okay, the way the current flow is a triangle starting from 0, 0, move to 2, 0, then it go to 1, 1, and then it's going to end at 0. So this how the current flow in the triangle. Okay, so it's given as I. So that should be the magnitude of the current from 0, 0, move to 2, 0, then move to 1, 1, then go back to 0, 1. So that's how the current circulates in the diagram. So what the question asks us, find H at 0, 0, 5. Okay, that should be the question of problem practice exercise 7.1. Given the current distribution, so we need to find H. So I think by now, so how we able to solve this problem by using Biot law. Okay, that's how we be able to solve this problem by using Biot law. Yet there are two main approaches that we can adopt. First, using basic method. So basic equation, so that should be one approach that we can use. Second, using previous solutions. Okay, so that should be two main methods that we can use under the category Biot-Savart law, either using basic method as what we have done before in our previous problem solving, or using a solution from our previous problem that we solved. Okay, so I think the best method is up to you, but for my case for this particular problem, I'm going to choose method number 2. Okay, so that's what I'm going to show to you. Hopefully from here, it's going to motivate you to do as many examples as possible, because what? From that experience enable you to become a wiser person when you want to solve EMT problem. Okay, so I'm going to use previous solution. So method number 2 is going to be by, so this is method number 2, previous solutions. Okay, what I'm going to do here, I'm going to state, we know standard solutions for finite straight filament current, okay, is what? H equal to phi I divided with 4 pi r sine alpha 1 plus sine alpha 2. And we have solved this problem together. And we need to relate this equation with triangle, okay? So the standard diagram that we should refer should be, this should be our source, okay? Let's say it's flowing from bottom to up, and then I'm going to draw my triangle now. So I'm going to do, let's say this is my point where I want to find my H. So what I have to define first is this particular line, Y. This is going to define our R. This is the R. So this is our on our diagram. How this line behave, we're going to make angle 90 degrees to the current source. Then we're going to define first angle alpha 1. Okay, angle alpha 1 is where referring to point where the current is starting, and then I'm going to create another angle where the current is ending, and I'm going to define this angle alpha 2. Okay, so therefore that should be my method now. I have to draw this triangle. Okay, so let's draw that based on our problem. So I think I have to add something due to side number 3. Okay, so the question asked purposely due to one side. So this is side number 1. This particular side is known as side number 2, and this the last side is known as side number 3. So we just want to find what is the H at this location due to this side of the triangle. Okay, so I'm going to draw that. So I'm going to draw this diagram relate to this problem. So I have to make it in 3D now. Okay, 3-dimensional. Oh, the ink is gone already, so I cannot use my red color pen already. So this is my x-axis. This is our y-axis. And this is our z-axis. So first I'm going to draw the triangle, the current source first. Okay, number 1 is position 1. Let's say this is position 1. So these two points going to join together here. So the straight line going to be, so this acting as my side number 3, I. what I have done, I've already shown this part of the diagram here. So this should be the current source from this point to this point, which is referring to site number 3. Then I'm going to find my H at this position. Okay, so it's 5 here. So that should be the distance from the source. So now I have to see. So I can see now this line actually is this line here. Why? Because the angle between these two lines is 90 degrees. See? So this is what this line. So now this is my R. Okay, then I'm going to draw first where the current is starting here. So this is my line. So you can see, so this is my line now, is similar to this part of the diagram. And what angle should I give to this particular position? Yes, alpha 1. Okay, so that's what you have to do. When you want to use previous solution, you must be able to link your current problem to the general solution that you obtain from previous effort. So this is what we are doing here. So now, how I'm going to solve this problem. Okay, so my solution now. So I'm going to use this equation. Okay, so this equation is our objective. So therefore, I'm going to say now, okay, so I is given 10 ampere. So that's given by the question. And then I'm going to determine my R. So this is the R from the diagram should be equal to 5, correct? Okay, now I'm going to determine my angle now, alpha 1. So how do I determine my angle alpha 1? Yes, you can use theorem Pythagoras. So therefore I can see that what should be the length here. So I can say tangent alpha 1 should be equal to 1. Square root 2 divided with 5, correct? Because the length of this part of the triangle is square root 2, because this is 1, this is 1. So the distance here should be square root 2, and then the distance here we know is 5 due to the problem. Therefore, the tangent should be 2 over 5. Yeah? So that should be, okay, or we can say sine alpha 1 should be equal to 1. Now, if sine should be square root of 2 divided with square root of 27, because 25 plus 2 should be 27. So that should be sine alpha 1. How about alpha 2? From the diagram, alpha 2, we can see alpha 2, which is the angle referring to the upper or where the current is ending. Since the current is ending at this position, which is coinciding with the R, so therefore we can state that alpha 2 is equal to 0 degree or 0 radian, because it's parallel, because this line and this line actually becoming 1, so therefore angle alpha 2 is equal to 0. But one important thing that we must define our phi. I cannot use phi in my solutions because phi is correct when my current is located along the z-axis, because phi is rotational direction. But now our current is not along the z-axis but at this position. So I have to now use a general substitution. So for me to substitute the phi, I'm going to define to be by defining the cross product of unit vector of the current flow cross with the unit vector of the R. Okay, so what should be the unit vector of the current flow here? So this is the unit vector that we want to determine now. Good. Negative x, negative y. Remember, unit vector must always divide by the magnitude. That should be the unit vector of this vector. Because this position is 1, 1, 0. Here is 0, 0, 1. So this vector is actually minus x over, minus y, and then divide by square root of 2 because unit vector. So that's done already, but we have to now what should be the unit vector of this line now, joining the source to the point of H. So from this diagram, we can state that the unit vector of AR should be unit vector Z. Okay. So now let's do the cross product. So negative X cross with Z will give us what? Yes, good Y. And negative Y cross with Z will give us negative X. Yeah? So that should be our solutions. So now, finally, we can set the H now is equal to, okay, the phi is equal now minus X plus Y divide with square root of 2. That should be our phi. So that should be the solution. And then I should be equal to 10 divide with 4 pi multiplied with R, which is equal to 5. And then sine alpha 1 square root of 2 divided with square root of 27 plus 0. Okay, ampere per meter. So that should be our solutions. So again, what the main objective here, just to show you we can solve the problem using our previous experience, previous solution, rather than we go back to the same basic method that we defined in the first stage when we adopt Biot as the method to find our magnetic field. Okay, so that should be my main objective. So that's what, as a conclusion here, you must always try to do as many examples. So by doing that, you can think, okay, many alternative method that you can use rather than only one basic method that we seen before regarding Biot law. Okay, that should be the first problem that we want to solve. So alhamdulillah, we able to do it. Okay, now so we have talked that the source for magnetostatic not only based on filamentary current, it can also due to a surface current and also volume current. So I'm going to go to the second type of source, finding H, which is due to surface current. So to do that, I'm going to do another problem here. Okay, this is also taken from our textbook. Okay, so hope you can see the problem here. Okay, so problem practice exercise 7.4. That's what we're going to do. Okay, so so the solenoid now of figure 7.9 has 2,000 turns, a length 75 centimeter, and a radius of 5 centimeter. If it carries current of 50 milliampere along the phi direction, find H along these 3 different positions. So you have solution there, so you can compare your solution with the answer given by Sadiku. Okay, so what we're going to proceed now, practice exercise 7.4. Okay, so given a solenoid, so you have a solenoid now. So I'm going to draw my solenoid. Okay, solenoid is very straightforward structure. So what is a solenoid? Is a cylindrical structure. Okay, I'm going to draw having length. Okay, this is a solenoid. So what actually appear here is there's a number of turns of conductor in this particular shape. So you have many turns. So let's say This is a part of this. So I'm going to draw as such. So meaning you have many turns circulating the cylindrical structure. Okay, so let's define here n turn. So that should be the number of turn of winding on the cylindrical structure, and then each turn is carrying a current I. Okay, so therefore that should I current and n turns. That should be regarding the solenoid, and then given by the problem, the solenoid have length L, and then radius A, even though given values, okay. And then I'm going to relate this problem to the axis. So let's assume now the axis of this solenoid is coinciding with our z-axis, and then the bottom part of the solenoid is located on the xy plane. Okay, let's state that. Okay, x, y, and z. Okay, so that's how we link the problem to a coordinate system. We attach the problem to a coordinate system rather than making it float. So by defining where the origin is in the diagram. So solenoid given, so the value given, okay, so let's say just now n equal to 2000 turns. So let's define it. N equal to 2000 turns. And then given L, the length equal to 75 centimeter. The radius is equal to 5 centimeter. And then I is equal to 50 milliampere. And then it rotates along the phi direction as shown in the diagram. So now, so let's change slightly the question rather than we give specific problem. So let's say find H along the z-axis. Okay, so let's make it more general rather than we try to answer Sadiku question, because Sadiku asked at a specific position. So let's make our solution general. So later on we can substitute the specific position asked by Sadiku into our general solution that we obtain here. So that's what. So we will just make it the problem becoming more general by stating find magnetic field along the z-axis. Okay, so how we do this problem, how we solve the problem. Okay, so I think most of you will say that, okay, this is our solution now using Biot-Savart law. Okay, that's good. And then we know that there are two methods that we can adopt. First, basic approach. Second, experience or previous solutions. Okay, so inshallah in this particular problem I'm going to do both methods. So reason why, because we haven't solved any problem regarding surface current yet, so that's why I'm going to use basic, and I'm going to do the second method here just to verify my solution that I obtained using the first method is agreeable to each other. So that's the way I'm verifying my solution is correct or not. Not by looking at my friend's solution. I must have decided using various methods. So if I got the same solution, alhamdulillah, my first method solution is correct. So that's what I'm going to do here. Okay. So let's say I'm going to do method number one, basic method. So what Biot-Savart state? Okay, Biot-Savart state that dH equal to sample current. I'm going to make it general first. Cross with AR, divide with 4 pi r squared. Okay, that should be our basic Biot-Savart equation. So now, where is my sample now? So my sample must be defined on this cylinder, because surface current, remember the way we define surface current must be on the surface. So I'm going to state now, because this sample is not fixed, I have to define the height now. So let's say I'm going to define the height to be Z prime. Okay, why? Because I want to find the H here, where I'm saying now the H is located at position Z. Okay, Z from the XY plane, Z prime from the XY plane. So therefore I have two positions to consider: position of my H location, position of my sample location. Since they are having different height position from the XY plane, I have to define both height using different symbol, yet I'm still stating that my primary symbol I'm referring here is Z. Therefore, I'm giving this height as Z and this height as Z prime, just to show the difference between them. So that's what. Now, how do I define my sample? Where, okay, sample current should be equal to what? Yes, J S ds. Remember our model? So which one is the vector? Good, the Js. Okay, so let's define in much more detail now. So what is current density? Remember the unit of Js that we defined in our discussion? Anyone remember the unit for Js? Good, ampere per meter. So how we define ampere per meter here? So I can see from this diagram, referring one side of this diagram, one part, okay, this particular part of the diagram, I can see current coming out along this particular side of the cylinder, current going into. So therefore I can see total current coming out is N multiplied with I. Total current going into is N also multiplied with I. So now I'm going to say it's going to be Ni. Okay, that should be the total current per side coming out from the paper, going into the paper, and multiply with I. So I can see that's referring to ampere, okay? And then meter. So therefore must be divided by length. I can say, okay, what affecting here? I can see, okay, the length is L. Okay, therefore, by doing that, I'm saying now this Js actually ampere per meter, referring to that diagram. Okay, this side, total current is Ni, and then the total length is L. Therefore, by doing that, I'm determining the unit vector ampere per meter. And remember, it's a vector. So therefore, the vector is the way the flow, as given by the question, should be along the phi direction. So that's done. That's how I'm defining my Js. And then my ds, standard from our cylindrical coordinate system. Okay, the height here, and then the width here. So let's do the mathematics now. Should be A d phi dz prime. Okay, that's how we define our Js ds. So you can see now it's going back to the basic concept that we talk about in week number 1, when we talk about coordinate system and calculus. So therefore, in EMT, that is what you have to always remember. Whatever you learn now, going to affect what you're going to see later on in our lecture. Okay, that's done. Alhamdulillah. So what else we need to determine now? Okay, the R. So how we defining the R? Remember, I have to join our sample to the location of our H. So that should be our vector R. Okay. Now, from the diagram, our R is equal to what? Similar to the ring that we have done before, minus AR plus Z minus Z prime Z. Correct? That should be our R. So now the magnitude R should be equal to the square root of A squared plus Z minus Z prime squared. Okay, so now, therefore, what we can do now, our DH now actually is equal to, okay, N I A d phi dz prime over L. Okay, in phi directions, I'm going to cross now with minus A R plus Z minus Z prime Z. All divide with what? All divide with 4 pi A squared plus Z minus Z prime squared, power of what? 3 over 2. Okay, that should be just simple substitution from what we already obtained information from the diagram. So let's proceed. Now we're going to do the cross product now, the first cross product. Okay, phi cross minus R. Okay, phi cross minus R will give us what? Good, Z positive. Okay, and then phi cross Z will give us what? Phi cross Z will give us R. Okay, so that should be our solution, meaning the H component of this sample can be divided into two, which consists of the Z component and also the R component. Yet, from our previous example, we know that when we do the integration, okay, let's say I want to find my H, which component going to be cancel out from the properties of the sample here, because we define the sample at this location, giving H as such, can be divided into two terms, the Z term and the R term, and due to the nature of our source, we can determine a sample which is opposite to our first sample. The second sample also going to produce its own magnetic field, and it also going to contain two components, R and H. So when we do the integration, that we are summing the field, so we can see that the R component will cancel out, correct? And the final solution after the integration will only be in the, yes, Z term. So I'm going to take the Z term now. Okay, Z. So I'm going to ignore the R term. So what's going to be N I A squared, okay, that's done, over what else? 4 pi L, agree? That should be, and then I'm going to do my integrations. First with respect to dq, then with respect to dz prime. Divide everything with A squared plus Z minus Z prime squared, power of 3 over 2. Okay, the limit now, 0 to 2 pi, 0 to L. So that should be what we should do. Okay, you can see how simple it is, just ignoring the R term due to what we have observed from our previous solutions. Of what? A ring, a single ring on the XY plane. I think that should be our third example that we did in my previous lecture regarding Biot. So please watch that video to see the justification why here we only consider the Z term to be at the end of the integration, and we're going to ignore the R term. Okay, so I'm going to solve the mathematics now. Okay, I'm going to say Z, okay, and then Ni A squared over 2L, correct? Because if I integrate this term, I'm going to have 2 pi. 2 pi and 4 pi will give me 2. Okay, that's done. Then I'm going to integrate the second part, which is this term. I'm going to use table now. Okay, so table will sit to me Z minus Z prime. Since I can see negative there, I'm going to put negative here. Divide everything with a squared. Square root of a squared plus Z minus Z prime squared. The limit from 0 to. Okay, so now I can see from this simple mathematics, the a squared term can cancel out. Okay, so therefore my final solution will be, which is equal to, okay, Z Ni over 2L, okay, should be Z over square root of a squared plus Z squared, correct? Minus Z minus L square root of a squared plus Z minus L squared. Okay, ampere per meter. So that should be our solutions, using basic Biot method. And you can see it's repetition. So it's a repetitive task. We have seen the same method being used when we solve magnetic field due to the filamentary current, either straight line or either it's a ring. So I'm just repeating it here. Okay. So let's check whether our result is correct or wrong by doing what? By not copying our friend's solution, by investigating ourselves. So we're going to choose the second approach now, previous solution. So what is I'm stating by previous solution? Remember when we solve this problem from previous example, previous example. So what is it? Remember that we have a ring located on the XY plane. Remember that problem? So this is X, this is Y, this is Z, and then we said that the current is I flowing in these directions, and the radius of our ring, alhamdulillah, coinciding with the A, which is similar to our cylinder radius, solenoid radius. So now we want to find the H located at the Z position. We know that the H from that problem is equal to what? Yes, Z, what else? I, A squared over, anyone remember? 2 A squared plus Z squared 3 over 2. Is it correct? Please check your solutions. Okay, so this is the H due to the ring. So now what we can comment, the ring here is appear to be similar to the sample of one ring here. Okay, I'm using the word sample. The ring here is appear to be similar to a sample behaving as a ring on our solenoid. So now, rather than we're going to take the sample to be a small sample area as such, now we're going to assume our sample is a ring sample. Okay, so that's the difference now. In this method, we assume the sample to be basic JS/DS, but using the previous solution, the ring solution we have obtained. So now we're going to assume our sample is a ring. Okay, so now, therefore, our ring sample, the current ring sample. Okay, now, let's see the difference now. Now the sample is a ring going to produce DH, because a sample always going to produce small h. So I'm going to copy, I'm going to set H becoming DH, because a ring now becoming a sample ring, but yet the pattern of the solution still remain. So now the pattern still remain, giving that Z, but the current is not I anymore, because sample current I'm going to state now DI. Okay, because sample H due to the sample current. And then other than that, everything remains the same. A squared divided with 2a squared plus. Okay, now I have to change slightly. Okay, since our height here is z, but now our sample height is good. Should be z minus z prime squared power of 3 over 2. Okay, so there you are. Okay, that's what you can see, logic behind our previous experience. You can use it and modify it, and then you can get a solution, inshallah. Yeah, so that they then go back to the basic. So this is a method for those who like to go for innovations. Because this is how you learn, because you innovate, you create, you force your mind to think, rather than just become like a robot, everything the same. Okay, so now, what about our DI now? And my DI here is equal to, okay, so I'm going to say total current and I over L. But now, as I can see, the sample have height dz prime. That should be my DI. Okay, you can ask me, why sir? Because, okay, what should be the unit of Ni over L? Ampere per meter, correct. What is the unit for dz prime? Meter. So now what should be the unit after you multiply these two components together? Ampere. Is it the unit for current? Yes, that's how you use that modification. So that's what in real engineering approach, unit is important. Unit will guide the engineer to choose proper method to solve their problem. So this is one example you can see. So now my DH should be equal to Z. Okay, and then DI now and IA squared over dz prime over 2L A squared plus Z minus Z prime squared 3 over 2. So if I want to find my H now, what should I do? Yes, just the H now should be the integration of the H, and then the integration of this term from where to where? 0 to L. And then you can see, if I modify the mathematics slightly now, just to show similarity now, it's going to be Z and IA squared over 2L. Integration of what? dz prime over A squared plus Z minus Z prime 3 over 2. 0 to L. And if you compare this mathematics and the one that we define up here, you can see it's the same. Okay, so therefore I feel confident my final result after integration will be exactly the same as what we have obtained using method number 1. Okay, so therefore this is what you always have to think in real problem of engineering, which always that we do not know whether our solution is wrong or correct. We need to find alternative method to verify our first approach that we took. So this is example. We have done the problem using basic, then we got solution to it, but we're not sure whether the solution is wrong or correct. Then we check it using another approach, and then by doing that, alhamdulillah, we confirm that the both method giving us the same results. Therefore, inshallah, what we are doing here is correct. Okay, this is how you look method to justify your result, even though we're not sure whether our solution is correct or wrong. Okay, I'm not going to use Savart to solve for the third type of current, which is volume current, because the mathematics involved going to be more cumbersome, which is triple integration. So, but yet I know there's a other method that we can use, which is similar to Gauss law, which is much simpler than Savart. And then the method is known as Ampere's second law. Inshallah, we're going to talk about this new method or alternative method in my next coming video session. So with this, I'd like to say thank you very much. Take care. Assalamu alaikum wa rahmatullahi wa barakatuh.